Have you ever held two magnets together and watched them attract each other? It's a pretty cool thing, but what's even cooler is that they can repel each other, too. How does it know which way to go? It seems almost spooky, like there's some unseen force at work. Well, there is, but it's not magic, it's science. And if you want to know how it works, all you need are a few household items and a willingness to get your hands dirty. Let's see how it's done. Now, magnets have been around for thousands of years, and we've always had a sort of intuitive understanding of how they work. If you bring one near a piece of metal, it sticks. Simple enough, right? But how do they stick? What actually goes on when you put two magnets together? And why do certain materials like iron and nickel seem to be more affected by magnets than others? To answer these questions, we have to take a closer look at the magnets themselves and how they interact with the world around them. So let's start out small, like really small. Here's a compass. It has a great example of how magnets work because its needle moves whenever it is placed in a magnetic field. But what's a magnetic field? Well, here's a hydrogen atom. Everything in the universe is made up of atoms, and this one has a nucleus in the middle, surrounded by electrons. Electrons carry a negative electric charge, and opposite charges attract. So naturally, we think the nucleus, which carries a positive charge, would hold the electrons in orbit around it. But quantum mechanics says no. In fact, those electrons exist in specific energy levels or shells around the atom. The innermost shell holds a maximum of 2 electrons, and each subsequent shell can hold a maximum of 8. But that still leaves something unexplained. Why don't the outermost electrons just fall into the second shell and stay there? Wouldn't that be the most energetically efficient state for the atom? Well, yeah, it would. And that's why sometimes they do, but other times they don't. And when they don't, something interesting happens. You see, in order for an electron to move between energy levels, it needs to absorb or emit a photon of light with the exact energy difference between the two shells. But some energy levels are forbidden. For example, there is no photon of light with an energy level that matches the difference between the first and second shell of a hydrogen atom. That means the electrons in the first shell can never fall directly into the second shell. They must fall into an intermediate shell before dropping down to the second shell. And when that happens, the excess energy is emitted as heat and light. But here's where things get weird. Those photons that get emitted have unpaired spins. That is, their angular momentum isn't perfectly aligned. This makes them what we call paramagnetic, and it turns out that every atom in the universe has some paramagnetism to it. Now, normally, this paramagnetism cancels itself out because the electrons are paired up, but sometimes it doesn't. And when that happens, we call the material ferromagnetic. Iron, cobalt, and nickel are good examples of ferromagnetic materials, and that's why they're attracted to magnets. Their atoms align with the magnetic field lines of the magnet. And now we know how magnets work at the atomic level. But we still don't know how they create a magnetic field in the first place. Well, imagine you're a tiny electron orbiting a nucleus. You're spinning, so you have angular momentum, and that creates a small magnetic field. Now imagine there's another electron spinning in the same direction as you. Your magnetic fields add together to create a larger magnetic field. Now imagine there's a third electron spinning in the opposite direction. Your magnetic field cancels out the third electron's magnetic field, and the result is a smaller magnetic field. This is the basic principle behind how magnets work. Their atoms are aligned in such a way that their magnetic fields add together to create a net magnetic field. Now it turns out that any moving charge creates a magnetic field, and that includes electric currents. A current is simply the flow of electric charges. So by passing an electric current through a coil of wire, you can create what's called an electromagnet. By varying the strength and direction of the current, you can vary the strength and direction of the magnetic field. Electromagnets are used in everything from doorbells to giant particle accelerators. They're even used to levitate trains. It's called maglev, and it works by using 2 strong electromagnets, one in the train and one in the tracks. The magnetic fields of the 2 magnets repel each other, which lifts the train off the tracks. Once it's floating, the train can move forward without any friction. Maglev trains can reach speeds of over 300 miles per hour. But how do you make a magnet? Well, here's a big chunk of iron. Now let's whack it with a hammer. That's not going to do anything. Iron is already ferromagnetic. It's naturally paramagnetic, but its atoms are randomly oriented, so the material as a whole isn't magnetic. Now let's take a piece of soft iron and wrap it around a coil of wire. We then pass a current through the coil, and the magnetic field of the coil aligns the atoms of the iron. When we remove the current, the alignment remains. Now we have a permanent magnet. Now, it turns out that some materials like aluminum and copper aren't affected by magnets at all. That's because their atoms don't have unpaired electrons. Even if you pass a current through them, their atoms don't align. These materials are called diamagnetic, and they completely lack any magnetic properties. Now, what about the Earth? Is it a giant magnet? Well, yeah, it kind of is. The Earth's core is mostly iron and nickel, and it's constantly churning due to the Earth's rotation. This motion generates electric currents, and those currents generate magnetic fields. The Earth's magnetic field extends thousands of kilometers out into space, and it's what compasses use to point north. But the Earth's magnetic field isn't perfect. There are places called magnetic anomalies where the magnetic field lines are distorted. These magnetic anomalies are caused by changes in the composition and structure of the Earth's core. For example, the magnetic field in this area of the Atlantic Ocean is weaker than the surrounding areas, which means that there must be something in the Earth's core that is affecting the magnetic field lines. One possibility is that there's a large deposit of iron and nickel here, and that is exactly what scientists found when they drilled into the Earth's S-crust and analyzed the rocks. This magnetic anomaly is called the Clipperton Magnetic Anomaly, and it's one of over 100 magnetic anomalies on the Earth's surface. Studying these magnetic anomalies can help us learn more about the Earth's core and how it works. And that brings us back to the question we asked at the beginning of the video. Why do magnets attract and repel each other? Well, remember how the Earth's magnetic field is distorted by changes in its core. Well, the same thing happens when you bring two magnets together. Each magnet creates its own magnetic field, and the field lines of the two magnets interact with each other. Where the field lines of one magnet are close together, the field is strong, and where the field lines of two magnets are close together, the field is weak. So the closer the field lines of two magnets are together, the stronger the attraction between them. And if the field lines of two magnets are far apart, then the field is weak, and the repulsion is strong. And that's why magnets attract or repel each other. It's not magic, it's science. And if you want to see more videos of me doing science, well, you're in luck.